my search space is only one-dimensional line, the line L over here. You see the line L over here. And in addition, I have M half planes, age 1 dot 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 age M. So age 3, for example, defined from this infinite line, and points in these half planes are only the points above this line. You see that they are above this line because this little fairy part is pointing toward the side of the half plane that you are willing to accept. So I'm looking for a solution for the one-dimensional linear programming that is a point on L that also satisfies all the half-plane constraints. It is a point on L which is inside the intersection of age 1 intersected with age 2 intersection all the way up to age M, because I need to satisfy all the constraints at the same time. I'll specify by Li, don't confuse with L. Li is a line that bounds age I. L3 is a line that bounds age 3. I'm looking at each half plane, and some of them contain the point way in the top. Like how high should I go? Go to infinity. Some of the half planes contain this point all the way to the top, and some of the half planes, on the other hand, contain the point over here at the bottom. In this example, age 4 and age 5 contain the points at the bottom, and age 1, age 2, age 3 contain the points right here at the top. And L is just a line, it's not a half plane. And I want to find the point that optimize my linear function, say as low as possible or as high as possible. So the algorithm for the one-dimensional linear programming, we discussed it in details last meeting, said the following. Let's ignore for the moment all the half planes that look downward, that contain the point 0 minus infinity. I'll only concentrate on the half planes that contain the point 0 and plus infinity. You might ask, what about half planes that doesn't contain neither, like vertical half planes that will be in your homework? At the moment, I'll assume that every half plane is one of these types, either contains point at the top or contains, and almost all the half planes satisfied it. So now I'm only considering the half planes pointing upward, and I'll compute for every such half planes age I. Li, remember, is a line that bound it, and Li intersected with L is just a point. For example, L1, the point that bounds the half plane that bounds age 1, and L intersect at a point, and let's call this point P1. And because of the way that these half planes look at, it's only willing to accept points above the line L1, then on L itself, this half length tells me only accept points to the right or above P1. Analogously, I'll compute P2, and because of the direction of the half planes, I'm only willing to accept points above P2. Points on L, not on Li, points on L, but above P2. Similarly, I'll compute P3. I denote it both as a point and as an open parenthesis. It means from the left side I'm bounding points to be only on the side of the parenthesis. Out of these three, which is really important, it's of course P2, which happens to be the topmost one, is the most important one, because if I'm satisfying the constraints of P2, then I'm also satisfying the constraints of P1 and P3, but not the other way around. That is, I'll compute out of the three values what is P max, the highest, the topmost, the uppermost point out of this set of points. And from now on, I know that my solution must be to the right of P max on L. That is somewhere along this ray L intersected with H2. Again, why H2? Because H2 is the one that corresponding to the rightmost intersection point. Analogously, I'm now looking at the half plane that looks downward. Look at their intersection of the line bounding these half planes with L, called it Q5 of Q6. Which one of them is more important? The lowermost one, the one with the minimum. So I will call it, I will look at the minimum out of all the half planes and say my solution must be somewhere in the intersection. Let's do it because the animation decided not to cooperate. So here is L, a few half planes that looks downward, each defining a closed parenthesis if you wish. Out of all of them, the leftmost one, Q mean, is what's important. That is, a point that satisfies Q mean satisfied also the other constraint that looks downward. Similarly, a few half planes that points upward define the three intersection points. The last intersection point is what important, that was P max. And where could the solution to the linear programming be? It should be anywhere between P max to Q min, anywhere in this region. And it's quite possible that along the way I will discover that actually here is L as before, here is Q min as before, Q min, the same Q min that you see right here. The same Q min that you see right here. Here is P max just as before, P max over here. And what is the feasible region on L? There should be points that are above P max but also below Q min, which tells you that there is no such point. Okay, then the one DLP should say there is no intersection, nothing common in between. In the first case, if you are looking for the lowermost point, your cost function is pointing, say, low downward or anywhere pushing you in this direction. You'll say this is my intersection point. Otherwise, I'll say this is my intersection point. One of the 2 points in the unique segment that is in the solution. We used it to construct an n-square algorithm for if we want to build the whole feasible region, or the polygon of all the possible solution to the LP, but today we will use it in slightly different context. Okay, how much time does it take? It takes the time would be some constant times m, if m is the number of half plane. Some constant, remember this constant, times n. Linear is the number of half planes that I have at this moment. As you'll see, m is not necessarily n. We'll use it in slightly different context. Everybody is good with how in linear time we can find the 2 critical points, Q min, P max, see how they relate to each other. So And I just have a little note saying that my internet is unstable. So yes, yell, and maybe I'll try to broadcast from my phone. Okay, time linear in the number of constraints. It's as simple as finding max and min. You just need to separate the half planes into these two groups. Another question that you can start thinking about right now, otherwise you face it in the homework, is of course what happens if one of these half planes is actually parallel to L. Possibly. They don't have any intersection points, and then you need to ask what is the meaning of this half plane. Let's move on. No, now it works. Amusing. Okay. Pmax, Qmin. Pmax tells you I'm on a ray that going upward. Qmin tells you I'm on a ray that points downward. And the intersection of these two rays is all you need to know. So let's start with an n² time incremental algorithm. Incremental here will mean that I'll start with two half planes and add another one and add another one and another one, and notice how my solution changes as I'm adding more and more half planes. And I'm only talking about the two-dimensional problem at the moment. So a few notations, and be focused because we are going to use this notation throughout this whole chapter. Age I is the ith half planes. My input is a cost function, let's say pointing downward, and n half planes, H1, H2, H3, and each half plane is bounded by a line, and let's give it a name. Li is a line that bounds or defines Hi. Li line that defines the half planes, H for half, the half planes, Hi. Think about Ci. Ci is a feasible region after I constraints are considered. That is Ci are all the points that the first food ingredient satisfies, H1, vitamin 1, and all the points that satisfies also the second vitamin, and all the points of the diet that satisfies the 3, intersection with age I. Note the I over here. So I can speak about Ci. Let's see a few examples. I will start by asking about age 1 and age 2. I only have age 1 and age 2. I always start with I equal to. So let's do it. Here is age 1, here is age 2. What is C2? What is a feasible region after two constraints? Not very hard. It is just everything in this infinite wedge over here. Now, a word of warning, I am not going to construct Ci explicitly. I can talk about it as a concept. There is such a thing. There is always a feasible region if it's not empty. But my algorithm is not trying to compute Ci explicitly. Okay, so what does the algorithm going to do if it's not going to compute the whole feasible region exactly? Well, out of all the feasible region, I only care about one specific point, namely the point that optimize my cost function. the points in the feasible region that optimize my cost function. Let's say that my cost function is pointing downward. That is, I want to minimize 0 times x plus 1 times y. My cost function tries to push me lower and lower. And out of all the infinitely many points at C2, I only care about V2. What is V2? The optimal vertex of C2. The optimal to my cost function that I have right now. My cost function points downward, then this is V2. Okay, let's insert edge 3, this green guy over here, and can somebody please tell me what is C3? So C3 is edge 1 intersection edge 2 intersection edge 3, and in this example, what is C3? It hasn't changed one bit. It's exactly what was a moment ago. The whole C2 was the whole wedge over here. That was C2. But now this whole wedge lies inside edge 3, so C2 is also C3, which makes our decision about what is V3. V3, by the definition, is the optimal vertex. Out of all the vertices of C3, tell me where is the vertex that is the best one to this cost function, the lowermost one. It's just V2. So V3 is nothing but V2. So we see that edge 3 is completely redundant. Let's move to edge 4. Now it's not true that C2 and C3 are the same thing, because edge 4 does eat something out of it. If it's not clear, I want to compute what is C4, which is edge 1 intersection edge 2 intersection edge 3, everything so far, intersected with edge 4. So the optimum, so the feasible region at the moment is the polygon with infinite rays that going all the way to here, turning in this vertex and continue all the way to infinity. Everything over here. Everybody agrees that this is C4. What is V4? V4 is the same, unchanged. So it's V2 equals V3, which is also V4. Because a new half plane, H4, doesn't really care or doesn't disturb V2. In other words, we can check that V3, which is this point, which is also V2, V3 is inside edge 4. V3, I'll use this notation a few times, is inside edge 4. It doesn't violate it. Edge 4 agrees, says, yes, as far as my fourth vitamin, this point is healthy enough as far as vitamin number 4. Everybody's happy? Everybody understands this notation because I'll keep using it. of this decision to pick a color. Brown, age 5. So now I want to compute what is C5, which are defined by the intersection of age 1, intersection age 2, age 3, age 4, and age 5. And my question is, what is C5 and what is V5? V5 is the lowest point on age 5, which is inside C5, which is this point. So this is V5. And age 5, by the way, is, even though the algorithm, as I said, does not compute the whole intersection, but just so we all know, C5 is this part. So in blue, this is C5. Make sense with everybody? One more. Green. We didn't have green yet. That we said is V5. And here is age 6. And what is V6 and C6? C6 is empty. There is no point that satisfies all the constraints. It's an over-motivated diet. It implies that no matter which combination of bananas and oranges you take, you cannot satisfy all the constraints. So C6 is empty. That's just a notation for empty. You cannot find any point inside C6. But I cannot be both below L6. L6, remember the line that defines age 6. I cannot be both below L6 and above the line that defines age 5. Okay. So hopefully everybody feels comfortable with notation. Let me go through it once again. I'm adding the half planes one by one, starting from, I start with two of them, so age 1 and age 2 I'll compute directly. Now from I equal 3, 4, 5, etc. At each iteration I'll add age I, I'll add age 5, and I'll ask how Vi is changing. Do I need to change it, or what is the optimum that I've seen so far? And just to proceed with the notation, age I is a half plane. Li is a line that tells me what is the border of this half plane. When do I move from acceptable diets to acceptable diets? Ci is a feasible region after I constraints. That is, Ci is just what we had written beforehand. You can also, if you want to look really fancy, you can write Ci is the intersection, like you write sigma. You can also write from I goes from 1 till I, sorry, K goes from 1 till I of age I, which is just like writing this is age 1 intersection age 2 intersected all the way intersected of age I. Okay, just a fancy way to use the intersection sign. It's fine if you're not aware of it. But remember the notion of the feasible region. We have the optimization function, but before we ask for optimization, we ask either any points in the feasible region at all. However, the highlight of the algorithms that we are going to see are that we will not worry very much with maintaining CI, that is when we are adding half planes, moving from AGI to AGI plus 1. We are inserting new half planes. We will not worry very much about changing CI, but we will care very much about updating the optimums that we see so far. The question would be, should I change the optimum or not? Yeah, so in the animation, you see I'm adding age 3, this bounded by the line, and C3 will be everything in this polygon or everything in this wedge. I think that the example on the whiteboard is more successful. Okay, theorem. At the ith state of the algorithm, at the ith state, when I'll start the algorithm, just pulling up the examples that we had beforehand. Here is V2, here is C2. C2 is the intersection of age 1 intersected with age 2. And now I'm going to move from the case of from I to I plus 1. I'm going to add one half plane, and I want to see how this one half plane change my solution. Again, I'm moving now from 2 to 3. I used to be 2, now I is 3. I know what is V2. I know conceptually what is C2. And I want to ask how my solution, the optimum solution, how V3 looks like, and how should I find V3 now when I'm about to add the third constraint, age 3. And in general, I'll move them to the case of from 3 to 4, from 4 to 5. Each time I will add one more constraint. So, theorem. Vi minus 1, in our case V2, maybe it's already inside age 3. That's the example that you see on the whiteboard. V2 is inside the half plane age 3. The half planes consist of all the points above the line L3, everything over here, and it includes V3. What is the optimum solution right now? Well, V2 was the best that I had before I added age 3, and the optimum that I had earlier, V2, doesn't contradict age 3. I will not be able to get anything better than V2 because I couldn't get anything better even if I had fewer constraints. The fewer constraints, the better it is for our cost function. So if V2 is inside age 3, then essentially you don't need to do anything, just change the labels of V3. You know what is V3, just the point V2, which might have been the point V1, might have been the point Vi minus 3, I don't know. But if it's not broken, don't change it. You're adding age 3. Age 3, I'm checking if V2 is inside age 3, and if yes, it's not broken, I'm not going to fix it. I'm just going to say that V3 in this case is nothing but V2. The old optimum is a current optimum. I definitely cannot get any better optimum, and the new constraint doesn't force me to take anything worse. Worse here meaning higher. Our cost function is to go as low as possible, so worse would be go higher than this solution. Okay, so the first part I think is quite obvious. The second part is less obvious. If Vi minus 1, the old optimum solution violates age I, is not in age I. Let's see an example. Here is age 4. Better. Here is age 4, all the points which are above this line. And V3 is definitely not in age 4. V3 is not in age 4. So now it looks like all the work that I've done so far doesn't help me at all. I need to start from scratch. So it's fine that I had a solution to some sub-problem, but now for the big problem, this is not a valid solution anymore. But that's a point to say, aha, but I still earned something from all my hard work. I know that there is, or possibly there is, a new optimum solution, and to look at the new optimum solution where V4 will be, it must be on L4. That's a theorem that we have to prove. We know that V4 must be, obviously, V4 must be inside age 4, of course, because it should be inside age 1 and inside age 2 and inside age 3 and inside age 4. It should be inside age 4. Okay? However, that's not what the theorem tells you. Not only that that V4 is inside age 4, but it's also on the boundary of these half planes, age 4. It must be on the red line. V4 must be on the red line that defines age 4. You don't need to use two-dimensional search anymore. Your world is now shrinked to be only the line that bound age 4, and the new solution must be on this line. Make sense? We don't need to solve two-dimensional problem at the moment. We can solve one-dimensional problem. The new solution is only on Vi must be on Li, the line that bounds age I. And how can I find it? I will use a one-dimensional linear programming. The one-dimensional linear programming, what did it take? It take a line. What will be this line? This line will be, in this case, V4 would be the solution to the one-dimensional linear programming, where what? The one-dimensional linear programming wanted to see one specific line. What this line is going to be right now? This line is going to be, if you believe the theorem, this line is going to be L4. Let's be color. Let's make an attempt to be a bit consistent with the color. Then L4. Solution must be on the line L4. And what are the half planes that the one-dimensional linear programming needs to see? Not all the half planes so far that exist in my database. Not everything from 1 to n. Only the half planes that I've seen so far, which are age 1, age 2, and age 3. I could have written here age 4 as well, but it doesn't have any impact once I know that I'm on this line. Okay, so in this case I'm calling the linear programming where the one-dimensional linear programming will look on the solution only on L4. And notice, it's not trying to say that every time that you are adding constraints, your solution will be on the line that bounds these constraints. Well, when I added age 3, the new solution is not on the line bounding age 3. It's really only, and that's quite surprising, it's really only because the new solution violated my previous optimum, then I know that the new solution must be on the boundary of the previous solution. So let's prove this theorem. And I think that the proof is constructive enough, so even if you lost me in this description, the description of the solution will show you what happened. First case, if vi minus 1 is in hi, then the new optimum and the previous optimum are the same. I can ignore the hi. Not ignore completely, but at least it doesn't change my optimum. Let's prove the second case. So here is vi minus 1. Vi minus 1 is the lowest point in a bunch of half planes. Intersection of half planes, they define some polygon, I don't care who is whom. Here is vi minus 1. That was my best solution, a vertex of the polygon, at which my cost function optimized, lowest point, and it satisfies age 1, it satisfies age 2, it satisfies all the constraints up to age I. That is, age I minus 1 was the last constraint that was satisfied by vi minus 1. And here comes bad age I, and vi minus 1 is not in age I. Here is li, the line that bounds age I, and vi minus 1 is below this line, and the half plane wants to refer to only points above it. It's exactly the example with the red half planes with age 4. V3, which was also V2, V3, which is also V2, lies below age 4. So age 4 disturbing. And what am I trying to convince you is that what do you think that the new solution would be? Where is V4 in this example? Where is V4 in this example? Maybe it's intuitive enough in this tiny example. Where is V4? Where is V4? It is satisfied by age 3, satisfied by age 1 and age 2, and also satisfied by age 4. So I'm trying to go as low as I can, and what disturbs me from reaching all the way down to V3? I have to, as I'm going downward, I have to land at some point on a point of L4. You're falling from heaven down into V3. You will, along the way, you must hit the floor of age 4. That is, you must hit V3, and that's why the new optimum solution will be on L3. Will be actually, this point is V4. So let's see the general scenario. Here is Vi minus 1. That's the lowest point that I could reach before age I appeared. Next, age I showed up, and Vi minus 1 is not in age I. What the theorem tries to tell us, that the new solution, Vi, must be on Li itself, on the floor of age I, on the line Li itself. Let's assume that the theorem is wrong. Assume by contradiction that I'm lying, and actually Vi is floating somewhere. Well, it's inside age 1, inside age 2, inside everybody, including age I, but it's not on the floor of age I. It's not on Li, so it's just floating somewhere in the interior of age I. Make sense? That's the opposite assumption to Vi is on Li. I'll assume that it's just floating somewhere. And obviously Vi, the optimum solution of everybody, is inside all the half planes, including age I. What about Vi minus 1? It's inside all the half planes, excluding age I. Why excluding? Because I know that vi minus 1 violated age I. I had to change the optimum to upgrade it to something that was actually not as good as vi minus 1. Now, look at this segment that goes from vi minus 1 all the way to vi. Well, it happened in the picture, but it will you can easily validate that it's true in general. What happened to my cost function along this segment? Say if I'm trying to look for the lowest point. Obviously, vi minus 1 is better to the cost function than vi. More constraints, meaning I'm not as good, cannot hit the same optimum because I have more rules to obey. And I didn't lose any rule, I still have to obey the old rules. So vi, if I'm looking for just the height, vi is higher than vi minus 1. Again, I'm trying to get as low as possible. vi is higher than vi minus 1. vi is inside all the half planes, including age I. vi minus 1 is inside all the half planes, excluding age I. Meaning that if I'm walking along this segment, falling from vi to vi minus 1, what happened to my cost function as I'm gradually going down? My cost function is getting better and better because I'm asking how the lower the better. It's a linear cost function, so its gradient is always the same. Keep on going, keep making tiny steps, you keep improving your cost function. Your y value is becoming better and better. But now, because of convexity, how come that vi is inside age I? Vi minus 1 is outside age I, meaning that this segment must hit the boundary of age I at some point. This red vertex must hit the line Li. Let's call the point of intersection Q. Q is better than Vi to my cost function. Q satisfies all the constraints, including age I. It satisfies all the constraints. Why does it satisfy age 1? Help. How do I know that Q satisfies age 1? Somebody. Not a hard question, but you do need it to follow. How do I know that Q satisfies age 1? Because Vi lies inside age 1 because it's in the intersection of all the half planes, so Vi is inside age 1. Vi minus 1 is also inside age 1. What do we know about convex shapes? If I have 2 points that are inside age 1 is convex, then the whole segment between them is also inside age 1. Every point of the segment is inside age 1, and inside age 2, and inside age 3, and inside yada yada, all the way up to, not including, age I. All the segments is inside Ci minus 1, but this Vi is also inside age I. Vi minus 1 is definitely, I'm sure, not inside the age I. So as I'm walking along the red segment, at some point I must exit from age I, and this point Q at which I'm exit, it's better to the cost function than Vi. So Vi was not the optimum. Q satisfies everything that Vi satisfies, but Q is lower. We're trying to get as low as possible. So the new optimum solution must be on Li itself. It cannot be floating in age I but not on its boundary. Implying that the new solution, you don't need to look for it in a two-dimensional world. It's enough to look for the new solution only on Li itself, and call the one-dimensional linear programming that is much simpler. And by the way, when we'll talk about three-dimensional linear programming, that would be the time that we'll call that will say, I'm looking for solution in 3D, but I will solve it by calling the linear programming in 2 dimensions, which in turn we'll call the linear programming in 1 dimension. And voila, that's how we change our problem into simpler and simpler problems. So far, conclusion is that going back one slide, you're adding age I. If vi minus 1 is in age I, don't touch it. Just call it vi, the new optimum solution, but the point is the very same point. Otherwise, if vi minus 1 is not in age I, then it's sufficient to look for vi on Li itself using the 1D LP. And there is another conclusion here. The one-dimensional linear programming, what does a one-dimensional linear programming tells us, say, if look at this case, age 1, age 2, just as before. And here is age 3. Where is V2? Here is V2. Where is C2? This is C2, intersection of age 1 and age 2. Is V2 inside age 3? Is V2 inside age 3? Age 3 is anything below this line. Question mark? No. V2 is above age 3. Age 3 is anything above this line, so V2 is not inside age 3. So what does the theorem that we just studied, what does it tell you? It's enough to look for a solution only on L3, only on the line that bounds age 3. So let's do it. Let's look at the solution on L3 itself. So I need to cut L3, this line, with age 2, which will be this intersection point, meaning that my solution should be to the right of P2, but I'll also look at age 1, compute the intersection point, and this half length age 1 tells me your solution needs to be to the left of P1. Again, your solution should be on the line L3 to the left of P1, but to the right of P2. Which point should I find over there? Absolutely none. There is no intersection, so the 1D LP tells me there is no intersection on the line L3. But the theorem told us any solution, if you find one, must be on this line. Conclusion, that's a good time to tell whomever that designs the input, you did a crappy job. There is no point in common to all the half planes. That's exactly where I realized that there is no point in common. I'm calling the one-dimensional linear programming, but it says the max and the mean, the max and the mean, instead of looking at each other like this, they are looking at each other like this. I'm going to be to the left of this point, but also to the right of this point. So that's a good time to stop and say, to stop the algorithm and says there is no optimum solution. So I don't need to even work about age 4, age 5, age 3, age 6. I already realized that even after 3 half planes, there is no solution. Let's continue. So what is the algorithm right now? It's the same. The theorem itself boils down to be a very simple algorithm. It's almost word by word. I pick the first half planes, first 2 half planes. There is a P missing. I take age 1 and age 2. I look at the intersection, call the intersection V2. That's the optimum solution for the case I equal 2. And now for I goes to 3, 4, 5, dot, 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 n, look at vi minus 1, the old solution that you had for the I minus 1. If I equal 3, you are looking at v2. Look at v2. If it is inside age 3, you don't need to do anything. Then vi and vi minus 1 are exactly the same point, and you don't need to do anything. Correct? Just call the old solution the new solution, and then you can move to the next case for I plus 1. Else, that is vi minus 1 violates age I, then the new solution must be on Li, the boundary of age I. Vi must be on the line Li, and you're just calling the one-dimensional linear programming to find it. What do you tell the one DLP? Li, I'm only looking for solutions which are on the line Li, and satisfies all the previous half planes age 1 dot dot dot, age I minus 1. Okay, and if the one DLP doesn't find any solution on Li itself, then there is no solution at all, and you can stop the algorithm. It says the feasible region is empty. That's all. So that's almost the whole algorithm. And if the linear programming does give you a solution which did not complain that it's empty, then Vi is just the solution that you got from the 1D LP, the lowermost point or the point based on the cost function. How much time does this whole process takes? Well, it is, let's think about this input. Here is age 1, here is age 2. Here is age 1, here is age 2. Here is age 3, age 4, age 5, age 6, age 7. What happened to my linear programming when I'm trying to find the lowermost point in this input? I start with V2, that is right here. I'm adding age 3. Age 3 violates V2, so I'm calling the one-dimensional linear programming that finds the new optimal solution V3 over here. And then I'm adding age 4, which violates a V3, so I need a new solution on the line bounding age 4, maybe this one. This will be V4. And this will be V5, and this will be V6, and so on. Every time that I'm adding a half plane, I need to call the one-dimensional linear programming. So how much time does it take? It takes, the whole time call takes 3. Let me add 1 plus 2 to make it more familiar sum. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus dot dot dot. And minus 1, because all of it times a constant that we said the one-dimensional linear programming takes a constant times the number of half planes that it needs to solve. What do we know about this sum? This is n times n minus 1 in this case, because I'm not going up to r, minus 1 half, which is theta of n squared. So it's quadratic algorithm, which looks really, really stupid because we already had quadratic algorithms that even compute the whole feasible region, not only the optimum point, but the whole feasible region. So why did I waste a whole hour to show you an algorithm that is even not that is more complicated than the n-square algorithm that I already showed you earlier? Well, because as we'll see next class, there will be a very, very simple trick that will take this algorithm, makes a very small changes of it, and then suddenly the running time will drop to n. Okay, so we are going to make a really tiny change of this whole code, and then the running time will drop from n squared, which would have been in 3-dimension n cubed, which would have been in 4-dimension n to the fourth. It will drop in each one of these dimensions only to linear time. However, not with 100% probability, just with probability of 99.99999, the running time will be linear. But I will need some good karma to make it. But in terms of changing of the algorithm, it's going to be a really, really cosmetic change. People, questions so far? Question about the grading of the midterm. We are done with class today. If you have questions for the midterm, I'm happy to chat. No. Okay. Thanks, everybody. Bye.